Hello, sir. Assalamu alaikum. I am Muhammad Shahadat Hussain and my student ID is 21115144607. Welcome to our presentation. Today, our presentation topic is examples of evolutionary algorithm. So these are my team members and these are the contents that we will cover today. So let's start with a short introduction. What is evolutionary algorithm? Evolutionary algorithms are a family of computational methods inspired by the process of natural evolution, and they play a vital role in solving complex problems. As we dive into this topic, we will focus on real-world examples of how evolutionary algorithms are used to tackle diverse challenges, from optimization to machine learning. There are several evolutionary algorithms, and genetic algorithms is one of them. Genetic algorithms are a subset of evolutionary algorithm. They draw inspiration from the process of natural selection and genetic recombination. Genetic algorithms are designed to mimic the principles of evolution to solve optimization and search problems. These algorithms are highly adaptable and can be applied to a wide range of problems, making them one of the most versatile tools in optimization. Here is an example of genetic algorithm, traveling salesman problem. It is a classic problem in which a salesperson must visit a set of cities and return to the starting city while minimizing the total distance traveled. Genetic algorithms can be applied to find an optimal or near optimal route for the salesperson, reducing travel cost and time. They work by evolving a population of possible routes over generations, gradually converging towards an efficient solution. These are the steps of traveling salesman problem. The first step is initialization. Here we need to initialize a population of possible routes through a set of cities. In the next steps, we need to evaluate each route's total distance traveled. Then we must select routes based on their fitness value. Here we need to select two routes as a parents routes based on their highest fitness value. In step 4, we need to create new routes by combining segments of two parent routes. We can also call these steps as crossover. In the next steps, we need to apply mutation by swapping two cities in some routes. And the last step is we need to replace the old routes with new routes. If we find an optimal solution, our algorithm will be stopped here. But if we don't find any optimal solution, we need to repeat these steps for multiple generations. Over time, the algorithm converges towards an optimal or near optimal route for the salesperson. Now, I would like to welcome our next presenter, Gulam Kibriya.
Hello. Hello. My name is Gulam Kibriya. My ID is 21115145592. Now, genetic programming is a very classic application of evolutionary algorithms. Genetic programming is a remarkable member of the evolutionary algorithms family that extends the principles of genetic algorithms to evolve computer programs or symbolic structures. Genetic programming aims to find computer programs that solve a specific problem, making it highly versatile for tasks that involve manipulating and generating symbolic expressions. Unlike traditional programming, where humans design algorithms, genetic programming uses a population of candidate programs and evolves them over generations to discover effective solutions. A very good example of genetic programming is symbolic regression. Symbolic regression is a problem where the goal is to find a mathematical expression that approximates a set of data points. Now, genetic programming can be applied to evolve symbolic expressions, allowing it to discover mathematical formulas that fit the data. It's particularly valuable in fields like data analysis, where finding concise and accurate mathematical models is crucial. The symbolic regression example demonstrates how genetic programming can automate the discovery of mathematical relationships in complex data sets. The way we would approach using genetic programming to solve symbolic regression problem is by using the classic steps used in evolutionary algorithms, which is we first have to choose a set of candidates that we're going to initialize the problem set with, which are candidate solutions, or in this case, candidate symbolic expressions. So we're going to have let's say 10 or 20 symbolic expressions that are already solving the problem, then we're going to use genetic programming to optimize those solutions and find a symbolic regression expression that approximates the solution best among those 20 or 10, for example. So first step is we're going to start with an initial population of mathematical expressions. And then, so these are our candidate expressions. And then we're going to evaluate the expression's fitness by comparing their output to the desired output. So we already have an output that we desire. Now we're going to test all those candidate expressions and see which candidates expressions give the best result. And based on the results, we're going to rank them and we're going to evaluate them. Like we're going to evaluate them and then we're going to rank them. And after ranking them, we're going to select expressions that give the best performance for the reproduction, because we're going to use these. So let's say we have 10 expressions and 5 of them did the best among those 10. We're going to choose those 5 because we're going to be using those 5 to produce our next child expressions that's going to be our next generation of expressions. So we're going to select expressions for reproduction based on fitness. In this case, better approximations are favored. Then after selecting the best ones, the ones that perform the best among the expressions, we're going to combine parts of 2 parent expressions to create new expressions or new child expressions. And after that, we're going to apply mutations. Now, we're applying mutations only because to introduce more diversity, because if we don't mutate our child expressions, we're not going to get any new information in them. So for example, if we have 10 expression candidates and we choose only 5, then if we keep crossing between those 5 expressions, then we're only going to be left with the properties of those 5 and no new properties. That's why we're introducing mutations, such as changing mathematical operators and constants in some offspring expressions. After mutating, we're going to replace the old expressions with the new generation, and we're going to re-evaluate these expressions based on their fitness again. And then we're going to choose among them the ones that perform the best, and then we're going to use them again to create new child expressions. And we're going to keep repeating this until 1 or 2 conditions are met. One is we provide a constant amount of generations that we want to get, let's say 30 generations. So it's going to run for 30 generations, or we get the result that we're looking for. So those 2 are the most usual terminating conditions. Now we're going to repeat these steps for multiple generations. And generative programming evolves mathematical expressions that closely approximate a given data set. Thank you. I'd like to invite my next presenter, Jahid.
Hello, I'm Mohammad Abusila Jahid. My student ID is 211151460. Now, evolutionary strategies. Evolutionary strategies are the subset of evolutionary algorithms that have their roots in the biology, especially in the field of evolution and adaptation. Evolutionary strategies is known for its efficiency in optimizing high complex dimensional problems, particularly in a continuous domains. Unlike the genetic algorithms, evolutionary strategies typically doesn't use the recombination or the crossovers, but they heavily relies on the mutation operations. Evolutionary strategies employs a population candidate solutions and evolving them to adapt to their environment to find the better solutions. Now, here is an example, neural networks weight optimizations. We know that neural networks are the fundamental components in the machine learning and artificial intelligence. So evolutionary strategies can be used to optimize those weights of neural networks, critical steps that train them for a various tasks. Evolutionary strategies can adapt, optimize neural network weights, helping neural convergence faster and achieve the better performance. Those applications highlights how the evolutionary strategies in instrumental enhancing training neural networks, making it more powerful tools in AI and machine learning. So in the conclusion, we explored the fascinating world of evolutionary algorithms and their diverse applications in solving real-world problems. We began our journey with genetic algorithms, which mimic the process of natural selection to optimize a wide range of problems. as demonstrated in the traveling salesman problems. Then we delved into the genetic programming, showcasing how it evolves computer program to solve complex tasks like symbolic regressions. Then we evolutionary algorithms in our list, emphasizing their role in optimizing continuous domains, particularly in an applications like neural networks with optimizations. So that's it for our presentation. I hope you enjoy it. Keep me in your prayers. Assalamu alaikum. Thank you.